Welcome, everyone. Today, we are diving into one of the most fundamental concepts in research methodology, sampling methods. If you have ever wondered how scientists, pollsters, or quality control experts can make highly accurate claims about millions of people or products by only testing a few hundred, you are in the right place. We will build this understanding from the ground up, starting with simple intuition and moving all the way through the mathematical formulas that make rigorous research possible. Let us get started. To begin, let us think about a very familiar everyday scenario. Imagine you are cooking a large pot of soup for a family dinner. To check if the soup has enough salt, you certainly do not need to drink the entire pot. Instead, you simply stir the soup well and taste just one small spoonful. If that single spoonful tastes perfectly salted, you can confidently conclude that the entire pot is perfectly salted. This simple, intuitive action is the exact foundation of sampling in research. We take a small, manageable portion to understand the massive, unmanageable whole. Now that we understand the basic intuition, let us define our terms formally. In research methodology, sampling is the systematic process of selecting a specific subset of individuals from a larger statistical group. We call this complete, entire group the population. It includes every single person or item you want to draw conclusions about. The sample, on the other hand, is the smaller, selected group that actually participates in your study. The primary goal of any sampling method is to ensure that this smaller group is a perfect miniature reflection of the larger population, completely free of bias. Let us look at this concept visually. On the left side of your screen, you see a large circle representing the target population, denoted by a capital N. This circle is filled with many dots, representing every individual in the group we want to study. Notice the arrow labeled Random Sampling Method, pointing to the right. This represents our systematic selection process. It leads to the smaller circle on the right, which is our sample, denoted by a lowercase n. This diagram perfectly illustrates how a sample is simply a carefully extracted piece of the much larger population. This visual brings us to an important question. Why do we not just study the whole population? Measuring every single individual is called conducting a census. While a census gives absolute certainty, it requires massive amounts of time, money, and human resources that most researchers simply do not have. Furthermore, in fields like manufacturing, testing a product often destroys it. For example, if you're testing how much force it takes to break a car windshield, testing every windshield would leave none to sell. Therefore, sampling is absolutely critical. It allows us to make highly accurate scientific decisions while saving valuable resources. Now that we know why sampling is essential, we face a mathematical challenge. Before we actually select our sample, we must answer a very important question. Exactly how many people or items do we need in our spoonful to be accurate? If our sample is too small, our results will be random and unreliable. But if our sample is too large, we defeat the purpose of sampling and waste time and money. To find the perfect balance, researchers must decide how confident they want to be in their results and how much inaccuracy or margin of error they are willing to accept. To calculate this exact balance mathematically, researchers use Cochrane's formula for sample size, which you see on screen. Let us break down what each symbol means. The variable n represents the required sample size we are trying to find. The symbol z represents the z-score, which is a statistical value tied to how confident we want to be. The variable p represents the estimated proportion of the population that has the trait we are studying. We often set this to 0.5 to be safe. Finally, e represents the margin of error, which is the maximum inaccuracy we will accept. Notice that if we want a smaller margin of error, the value of e decreases, which makes the required sample size n increase significantly.
Let us see this formula in action with a concrete example. Imagine you want to know the percentage of citizens in a massive city who support a new law. You want to be 95% confident, which gives a z-score of 1.96. You want a 5% margin of error, so e is 0.05. Assuming maximum variability, p is 0.5. We plug these values into Cochrane's formula. First, we square the z-score to get 3.8416 and the margin of error to get 0.0025. Multiplying the numerator terms gives 0.9604. Dividing this by the denominator gives 384.16. Since we cannot survey a fraction of a person, we round up. Our final answer is 385 citizens. Now that we have successfully calculated a sample size for a massive city, let us consider a slightly different scenario. Cochrane's standard formula assumes the population is infinite or extremely large. But what if you were surveying students at a small private college with a total population of exactly 1,000 students? Our previous calculation told us we need 385 people. However, surveying 385 students out of just 1,000 is a huge chunk of the population, and it is unnecessarily large to achieve our desired accuracy. When our total population is small and known, the initial formula overestimates how many people we need. Therefore, we must mathematically adjust our sample size downwards. To fix this overestimation, we use the finite population correction formula. This formula takes our initial sample size calculation and scales it down based on the actual size of the total population. Let us look at the variables. The variable n subscript adj represents the new adjusted sample size that we are trying to find. The variable n is our original calculated sample size, which was 385. The capital N represents the total known population size, which in our college example is 1,000. By dividing our original sample size by a factor that includes the total population, we will mathematically reduce the number of people we actually need to survey. Let us apply this correction to our college scenario. We substitute our original sample size of 385 for n and our total population of 1,000 for capital N. First, we look at the fraction in the denominator and subtract 1 from 385, giving us 384. We divide this by 1,000 to get a decimal value of 0.384. Adding the 1 gives a total denominator of 1.384. Finally, we divide our original sample size of 385 by this new denominator. The result is 278.17. Rounding up to the nearest whole person, our final adjusted sample size is 279 students. We achieve the exact same accuracy while surveying fewer people. We have covered a lot of ground today, so let us summarize the most important ideas. First, sampling is an essential technique that allows us to understand massive populations by examining a small, perfectly representative group, saving immense time and resources. Second, we do not just guess how many people to survey. We use mathematical tools like Cochrane's formula to calculate the exact sample size needed to guarantee our desired level of accuracy and confidence. Finally,
If we are studying a small, known population, we apply the finite population correction to avoid surveying more people than necessary. Mastering these calculations empowers you to conduct highly rigorous scientific research. Thank you for watching.